Welcome to another video in our series on introducing preference heterogeneity in discrete choice models. Our last video covered the basics and how we can use interaction terms and random coefficients to introduce preference heterogeneity. These enhancements make our model more realistic in its predictions of how consumers would respond to different policies. But before we can do any estimation, we face a fundamental identification challenge. How do we know if differences in choices across consumers arise from different idiosyncratic preferences that each consumer had at that particular moment that they made the choice, versus how do we know that consumers differ in terms of their preferences that are inherent to the choice being made? Stated more succinctly, we can think of the unobservable part of preferences as containing an individual specific component and a purely idiosyncratic component, and we need to be able to distinguish between the two. In this video, we'll discuss different ways of solving this identification puzzle. Let's start with our familiar math from many videos ago. We have our total utility, capital U, is the combination of observable utility, little u, and unobservable utility, epsilon. And let's just pretend for a moment that this epsilon can be decomposed further into person-specific factors, eta I, and purely idiosyncratic factors, nu ij. Now let's write out the formula for the parameters for our observable component. So little u can be written as x beta plus z gamma. And for now, we're introducing bars over the parameters to emphasize that these are the same parameters for every person in our population. Now let's do a little bit more math, and let's try and bring those eta terms into their x and z components. So we can redefine eta as being x times delta plus z times phi. And then we can bring those terms in so that we have an average component, that's the beta bar or gamma bar, and an individual component, that's the delta I or the phi I. And then we can instead say that these delta I's or phi I's are random draws from some distribution that's respectively centered on beta or gamma. And so our final mixed logit model will have individual subscripts on these parameters, emphasizing that the parameter value depends on the individual. This is the basic mixed logit model, where we've added mixing distributions that are normally distributed on the betas and on gamma. So there's different ways that we can identify these parameters. So the parameters that we want to estimate in this model are beta bar, sigma squared beta, gamma bar, sigma squared gamma. Those are the parameters that will tell us about substitution patterns and all that stuff. Now, we could identify this by just assuming that the distribution is actually normal in the population and then estimating the parameters accordingly. We would call this parametric identification, which just means that we're going to assume a functional form, and that functional form is going to give us the identifying assumptions and behavioral assumptions that we need in our model. Many people don't like this because it's not a data-driven way of performing the identification. We're not being flexible enough. If there's any amount of deviation from the parametric assumptions that we're making, then that would result in our model being misspecified and potentially being misleading. So this parametric identification just basically pushes the problem back one level, and it's something we can't formally test, and so we're just kind of have to make the assumption and see where it takes us. We might not like where it takes us, but that's what we've chosen. So the critical question of identification is, how can we know if the variation in observed choices comes from the eta I or the nu ij part of preferences? That's the critical question. If we have cross-sectional data, it's going to be impossible to separate these unless we make a parametric identifying assumption, like I just said. We have that person A is choosing a different option than person B, but we don't know if that's because person A has fundamentally different tastes than person B, or if the random shocks of the choice situation resulted in that difference in chosen alternatives. If we only have one observation per person, there's no way to distinguish this. However, if we have panel data, then we can see multiple choice situations for the same person, and then we can start to get a sense of what are the preferences that are permanent for this person compared to these idiosyncrasies that are also contributing. So the idea is that if there's persistent patterns across different periods or different choice situations, then that's going to load on the permanent tastes. If there's more random variation in the choices across periods, then that's going to load on the idiosyncratic part of the tastes. And here we've added a t subscript for epsilon ijt to emphasize that this is across multiple time periods. And the key assumption that we need to make any kind of identification argument in this scenario is that these tastes, these delta I and phi I, are stable across all the different choice situations that we see the person in. So basically the logic goes, the person would consistently choose similar alternatives across all the different situations if their preferences are loading on that delta I or phi I component. If we have more and more choice situations, then we're going to get better separation of these individual specific preferences relative to the idiosyncratic noise. And if we have an infinite number of choice occasions that we can observe, then we can perfectly identify each person's individual parameters. But we can also think about other forms of hierarchical data beyond just panel data. So different types of variation can be used to identify taste heterogeneity. It's not only panel data, but panel data is the most natural way to think about this, because in panel data we have the same person over multiple choice situations, and if we just assume preference stability, then that's a very natural and intuitive way to think about it. But there's another famous paper by Barry, Levinsohn, and Pakes called BLP. This was from 1995 in the journal Econometrica, and they're looking at a different form of hierarchy. They're thinking about markets instead of time periods. So basically in the BLP approach, we're looking at aggregate shares, not individual consumer choices, and we're looking at multiple markets. So the idea is that if I see similar stuff happening in similar markets, then I can chalk that up to more of the permanent part of the preferences. We want to look at within market, just like with the panel data approach, we want to look at within individual across time periods. We want to look at within market across products. So if there's certain substitution patterns there, then we can infer the distribution of delta I and phi I. There's also other options if we have convincing instrumental variables or exclusion restrictions of some kind. We can use those to also pin down the permanent part of preferences as opposed to the idiosyncratic or noisy part. There's a lot of papers in industrial organization that talk about all these situations. We're not going to get into that in this video series, but I just wanted to kind of open your mind to the fact that we need to establish identification when we want to start thinking about preference heterogeneity. And in order to do that, we need to first think about, can I infer this permanent component of preferences from panel data, or do I need some other identification setup to be able to allow me to separately identify the permanent and the idiosyncratic components of preferences? So there's lots of different ways of leveraging variation in the population data to separate these different components of the preferences, but the idea is that we need to be thinking about that from the get-go before we start estimating stuff. Now that we've established how we can identify these different individual specific preferences, let's now move on to estimation, which we'll do in our next video, and we'll formally introduce the mixed Logit model and talk about how we actually can estimate that. So I hope to see you in the next video.